Hello, everyone, and thanks for joining today's 5 non-obvious real-time data platform capabilities. My name is Matt Bushell, Senior Director of Product and Solutions Marketing at Aerospike. I'm joined here today by Mike Gualtieri, VP and Principal Analyst with Forrester Research.
Hi, Matt. Good to be here.
The topic for today, these non-obvious real-time data platform capabilities, the idea here is that these capabilities are not a simple checklist. And so I've invited Mike here to discuss and expound upon his experience in the industry and what he sees these capabilities are with clients that he's worked with and technologies and what it really means. So again, these are not meant to be simple checkboxes, but a lot of these capabilities are conjoined with additional capabilities or very rich capabilities. So with that, Mike, shall we get into it?
Yeah, sounds good.
Okay, so the first question I'd like to pose to you, or the first capability to get your reaction to, is cloud fluency. So people talk about hybrid cloud, they talk about inter-cloud, multi-cloud, but in terms of data platform capabilities, could you kind of describe, what cloud fluency means to you?
Yeah, and I think you hit on it when you said hybrid cloud as well within the cloud fluency phrase, because generally people think of cloud as the public clouds, GCP, Azure, maybe Alibaba, certainly AWS, and they talk about their cloud journey to those public clouds. And certainly we're seeing a huge journey by enterprises to those clouds. But there's two interesting things that I think are happening that expand this meaning of cloud fluency. The first is that large enterprises are already multi-public cloud. When we do our survey data and we say, all right, well, which clouds are you using? Turns out enterprises might be using a half a dozen different clouds. Now you think of the big three, but if you expand that to things like Salesforce and some other more SaaS platforms, those also are clouds. And wherever you're using a cloud, data exists. And it's reasonable to think that you're going to have to move data among those clouds for various applications, for example, machine learning. The second thing is this idea of hybrid cloud, or as I like to say, cloud anywhere. Technologies, container technologies, and then container orchestration technologies like Kubernetes have really provided a lot of portability options for applications and platforms such as databases. And that gives enterprises the option of installing applications and using data platforms on various platforms. Now, where we hear lots of enterprises saying, I am standardizing on Azure, I am standardizing on a particular public cloud, why would they want to be hybrid? Why would they want to go in their own data center or colo? There's three main reasons for that. One reason is that for regulatory reasons, jurisdictional regulations, that data may need to be in different places. So they may be in a different region, but they may need to be in a different cloud altogether. They may need to be in a colo, so private data center that they're renting space in. Second reason is machine learning and other types of analytical processes. It can get expensive, actually. So it's sort of counter to what you normally hear, because you say, oh, well, the most economical place to do certain data operations is of course the cloud. That's true for elastic workloads, because the elasticity in the cloud is tremendous. You pay for what you use. But what if you're running hot? What if you're running around the clock? Well, now you get people who are saying, whoa, my cloud bill is huge. I already have data center space that I'm using for other purposes, various purposes. So I want to run there. So there's this fluidity that enterprises want, this flexibility of running anywhere. And then the third thing for many enterprises is even edge. So the ability to use databases, to run data, to do data and analytics, to do transactions at the edge. It could be a kiosk. It could be autonomous vehicle. It could be a container ship. It could even be an airline or some local. So cloud per se shouldn't necessarily be thought of as just the big giant public clouds, but increasingly the cloud-like technology, Kubernetes and such, that can create clouds on any such infrastructure.
Yeah, no, it's yeah, a couple keywords you talked about there: flexibility, portability, and the fact that you may have even on-premises capacity available, things like avoiding lock-in, and then ultimately, running applications at the edge. Certainly, a lot of Aerospike customers do that today. So I think, yeah, Fluency, I think is a good, cloud is not monolithic, and there's a lot to it there to become.
Yeah, and Matt, there were some of the other evidence for this trend is well, in the past few years, right? There's been various startup companies that would say enterprises want to be in the cloud, so we're just going to be in the cloud, right? But then there's a large client that says, well, I don't want this to be in the cloud. So now there's multiple. So some of those companies have gone with multiple versions. Kubernetes, container-based technologies are making that easier to have both. But another evidence for this is the public cloud companies themselves. They hear their customers saying, well, maybe I'm not going to go all in. I'm not going to, for all the reasons that I just said and that we both discussed. And so you have AWS with Outpost, Azure with Arc, GCP with Anthos. Now, all of those aren't apples to apples sort of technologies or services, but all of them have to do with running cloud services outside of their clouds, right? So it's interesting that even the giant cloud companies who are saying cloud are saying, well, yeah, but you might want to do this outside of it. And that's a reaction, I think, to the demand as well. So cloud fluency, yes.
Yeah, well, Aerospike certainly has customers that do hybrid approaches as well. Let's it's a perfect segue actually, because there's something else you talked about that I think is a good second option for a non-obvious capability. And it could be described as almost like a combination of capabilities, but it is about managing data globally. So a lot of customers Aerospike has are very global. But the idea is that you want to manage your data globally, but also granularly. And one of the aspects with the data platforms such as Aerospike that we like to portend is with strong consistency. So a lot of times, data can be always available, but a lot of our customers and prospects we talk about, hey, I always want to make sure I have the right data, when it's being transmitted, and I also want to transmit, specific data. So could you talk about this global data management capability?
Yeah, and this is one of my favorites because Forrester clients are the largest of enterprises, and they generally are global corporations, and they have this issue of using data transactionally, analytically, globally. And essentially the problem with this, there's two key challenges. One is the speed of light, because when you start going over large distances, because you could say, well, I'm just going to transact and there's going to be one database and I'm just going to transact it there. But the speed of light does cause latency when transactions are continental. So there is the issue of latency over large spans. The second part of that is increasing regulatory issues where some data has to be local, but you need to use you need to analyze and find some of the meaning of that more globally to make strategic decisions and even tactical decisions about where your companies are. So consistency is critically important for those, but it has those two challenges. Now, from an industry standpoint, that's where things get even more tricky and where the granularity, as you say, matters. Financial transactions, cryptocurrency transactions, right? Those have to be consistent. And the technology to do that, you have to do that while overcoming the two challenges, which is the latency and any regulatory or data locality requirements. So both of those are necessary in a platform. What I found very curious is that this notion of eventual consistency was almost advertised like it was a benefit. Like, you know, you'd have these database vendors saying, well, it's, and you know, the great thing about this is that it's eventually consistent. And it was kind of like promoted like it was a quality. And really what they meant to say is that, well, we can't give you consistency, you know, we can't give you absolute immediate consistency, but eventually we can. And isn't that great? So certainly there are use cases for eventual consistency, and there are the realities of the world. Like, for example, you can think of disconnected devices and edge devices and other latency bottlenecks where
IoT
consistency is a strategy. But there's so many use cases where you have to have consistency, and it has to be global. Now there's challenges and techniques to overcoming the latency that the database providers have to provide. And then there's also the gathering of that data. I mentioned the idea that, well, we want to do some analytics or want to do machine learning models based upon this data. Well, how do you do that when the data is it has local regulations? You're not supposed to move that data out of the country, or it's cost prohibitive to do so. So imagine you're a giant e-commerce company and you're doing a ton of transactions and you want to refresh a machine learning model, a global machine learning model, every day or even every hour.
You don't want to
moving huge amounts of data. So some techniques for that would be federated learning.
Yeah. I was sorry for interrupting. I was going to say, you also don't want to ship the entire data set. You just want to ship the granular pieces that you need, again, to minimize the cost and also expedite the updated inferences, even at the edge.
Yeah, and in machine learning, federated learning, it will train the model locally on that local data. And that local data could be huge. It could be a huge amount of data. And then it ships that small part of the model back.
Yeah.
And then federated learning does is it creates, you know, in machine learning terms, an ensemble of these various local models to create one global model.
All right. So this is a good segue for kind of the next non-obvious capability. We were talking about size of data and being global, and the cloud kind of confers a lot of that. And it's something that can be described as predictable or even predictable high performance at scale, or really any scale. And so the contention is, well, a lot of NoSQL data platforms, you know, they have very high performance, but I don't know if you can talk to how that's not always the case at scale, or what you see, you know, how challenging is it to be predictably performant, you know, no matter the data set?
Yeah, I like how you phrase this as predictable performance, you know, versus just performance at scale. And when I think about scale, I think about two dimensions. I think about throughput, and then I also think about latency, right? So how much can I do? And when I do each one of those things, how fast can I do it? And you want predictability on both of those dimensions for two reasons. One, if it's a consumer application, e-commerce site, or some other type of site, that's going to have a direct impact on customer experience. So the more people using it, obviously, you want them to have the same experience. So that has just a direct impact on customer experience, which has a direct impact on business. The other is resource utilization of how I call this efficiency, right? What is the efficiency of the platform as well, right? Because you'll hear a company, I'll hear database companies boast of having 20,000 nodes or 10,000 nodes.
Yeah,
but what if you could do the same thing in 2,000 nodes?
Sure. Yeah, absolutely. Yeah. So it's, under the hood, it's not always the same. So
Yeah.
and I think you say that, you want to be predictable because, that these applications have kind of time windows to conduct what they do, for, particularly at the edge where it's very time constrained. So if they're not able to execute consistently, or in this case, predictably, you might get a fraudulent transaction, you might get a bad recommendation, you might miss a real-time bid. Each industry has its own kind of need for this predictability and in essence, cost. So you don't have to kill it with hardware, so to speak.
Yeah, and sometimes killing it with hardware, I absolutely agree. Those use cases are sort of similar to the use cases we talked about before. But I think the predictable use of resources as well to get that performance, and that's what I call the efficiency. But the other thing is that linear scale. I'm always careful of that when someone tells me that something scales linearly. I worry about what that means because there's been various research studies on various platforms that say, well, at some point there's chatter between the nodes, right? And sometimes that chatter. So that's why efficiency is also important as well, because nodes have to communicate in some way. And the more you have, the more volume you have, the more chatter you're going to have. So I think of efficiency in that manner as well. And if you're going to have predictable performance, you can't just have a vendor say, just add more nodes. That's not always the answer.
Wow, an inelegant solution to a scale problem. So one of the other counterbalances capability-wise is uptime, or really what could be described as uncompromising uptime. And so I might, in your experience, I might suspect that a lot of these solutions that kill it with hardware struggle with node birth and death quite a bit. They may not manage their nodes very elegantly either. And so that may kind of cause their systems maybe not to be up as much, or if they are, it's in a way kind of stressing the DevOps team. So in your experience, I'm kind of curious what, uncompromising uptime kind of means to you, and maybe the importance of it.
Well, I think, the importance question I've answered, you've answered, in some of the types of transactions we talked about, right? Bids, equities, in any type of transaction that's critical, even an e-commerce transaction. So the uptime is critical. The question is, what are the issues that create an environment where it becomes uncompromising? And I think the biggest so if we think about the cloud, here's what I hear some database vendors say. They say, well, AWS has 99.9 and Azure has this uptime and Google has this uptime. And they'll even pay you back if, service level agreements aren't made. But that's just the infrastructure, right? The database software itself is its own component with its own issues of uptime, right? All software has bugs. The underlying infrastructure can go down. How does that database handle it when infrastructure goes down? So I like to think of uptime as fault tolerance, not as an absolute goal. that it's going to be up, but that when something does go wrong, how has this database platform anticipated all the things that can go wrong? The underlying infrastructure it's running on, perhaps transaction loads that were not anticipated and planned for, configuration settings that maybe were not right for the application, and even bugs in the software. So things like, can the software have a rolling upgrade, for example, if necessary? So I think the best way for buyers to look at uptime is to analyze a vendor's fault tolerant strategy.
I think that's a good way to put it. And I probably should have prefaced the question as well that these real-time data platforms, such as Aerospikes, are really looking to be many things. A lot of times people have mainframes that have this speed, but aren't either distributed or not cost efficient based on the cost of MIPS, or relational database systems, which also are not distributed and don't have the performance. So NoSQL's capabilities, their Achilles heel historically has been this. So I think you're right, looking at how they manage fault tolerance to meet these others.
Yeah, and that the scope of the fault tolerance also needs to be larger than just the database. I've sort of done postmortems on many of Forrester's clients who have had performance problems during holidays and so forth. And they said, oh, we analyzed this would not go down. No, it didn't go down, but the service you called out to the credit card processor went down, right? So you have to look at all of the dependencies. So analyzing and being satisfied that a data platform will have uncompromising uptime. Make sure you understand what the dependencies are as well, because you have to analyze the fault tolerance as a system, not just myopically on one of the components.
All right. Well, I want to leverage that term analyze to kind of for the last non-obvious capability, which is something that we've only alluded to a little bit, and I know is particularly close to your areas of research, which has to do with machine learning, streaming at the edge, and transactional inferences at the edge. And so kind of the title of this last non-obvious capability is edge capabilities must include streaming and transactional inferences. And so I was wondering if you could talk about what that means for machine learning and kind of the fact that there might be two areas that are, two capabilities kind of combined into one here.
Yeah, I think streaming has become critical in modern applications, particularly for edge applications. Think of Uber. Think of Uber and Lyft. Those are edge applications, and these are real-time applications. So increasingly, a modern data platform has to have streaming capabilities. Now, what do we mean by streaming capabilities? There's two things. One is the ability to accept streaming information. Right. So basically the ability to have information pushed and to accept that and to store it. You might not have to do anything with it. Right. So it's simply the sheer ability to accept streaming information, which for some data platforms, which were designed for many like inserts and, an insert is sort of accepting of a streaming data platform, but streaming can be very spiky, and the throughput could be even higher than what databases were designed for. So the data platform has to be able to just be ingest. It has to get the ingest part of that correct. And in some cases, it may have to spit out a stream as well, right? Because as transactions come in, that it may have to put stuff on a Kafka queue or some other messaging bus. But there's another critical part of streaming, which is streaming analytics. And that's very different. That's analyzing data that's coming in on the stream. So analyzing what's happening in real time. This is a continuous query. It's a query that you're always looking at in that data platform, and you're looking for a threshold. You're looking for something that happens that indicates some sort of an action. Go back to the Uber Lyft example. You might be looking for when a car is entering a certain geographic zone, for example, or nearing a pickup, right? These are things that you're kind of looking at constantly in the streaming analytics case. Now, what you really have to think about is most data platforms are designed for a query and a response. So it's more like an ad hoc query. It's like, well, I think I will query this and then I will wait for the response. Whereas a streaming query is continuous and stateful. Yes. Because again, think of an IoT example where there's a device that has a vibration and temperature sensor. So you're not interested necessarily in just a threshold, like when the temperature goes to 79 degrees, but rather you're interested when that temperature increases rapidly over a 1 minute time period. Okay, that's a streaming analytic that has to be done over a time window. So it's sort of a time series query. Another example of that is in trading algorithms. You're looking for a certain volume of a stock to go up before you make a trade. That would be algorithmic trading. Again, analytics that are continuous. So a lot of real-time IoT edge applications will require not only the ability to stream information in, to be queried perhaps later, analyzed later, but to be ingested in real time and often analyzed in real time as well.
Not just simple queries, not just simple reads. I kind of refer to it as writes. You're kind of like, it's not easy to write at high throughputs, but then to, in essence, do something with it, and maybe something somewhat sophisticated or machine.
Yeah, Matt, this is something. I mean, I guess like a traditional or even a new data platform that is designed as a data warehouse. That technology is designed for full scan queries. Like, look through 1 billion records and tell me what the total sales are, right? That's the techniques you use to do that would not work if you're trying to do some of the examples I gave, the real-time query over a smaller data set, but a much faster moving data set and being done in real time. And I think you also asked about like transactional inferencing for machine learning. This is the other analysis part. So I described streaming analytics and detecting changes in the shape of data and maybe some statistical changes in it in real time. But machine learning is also about taking in streaming data or even transactional data and inferencing on the model. Inferencing, sometimes known as scoring, that basically means using the data and having a prediction. So a great example of this, I think, is a fraud detection. If someone's making a transaction, you might want to use that payload, that transactional payload, enriched with some other, say, customer data, and call a machine learning model right within the database platform to determine the likelihood of fraud. Why would you want to do that in the database? Latency. Because if you have to, a lot of people say, well, you just call out over here to this service or microservices architecture as if that's magical and fast. Not necessarily, right? So increasingly, when you have single-digit milliseconds for the entirety of a credit card transaction, for example, you're going to want to do that ML inferencing within the data platform.
Well, I also might suggest then I should have added a third dimension to this capability, which would be able to combine streaming data with historical data, and also to ship the ML models to the edge. So
that's a great point, because both streaming analytics and machine learning, the payload, the transactional data or the streaming payload that comes in, is likely not to have all the data that's needed to do the analytics and that the machine learning model needs. So for example, if it's some sort of consumer e-commerce thing that's coming off a mobile app, you're probably going to get the customer's ID, but the fraud, maybe you're going to get the customer's ID, the location, and the type of transaction, but the fraud model might need the customer's home address. It might need some geospatial information of where the phone is. And however long it takes to get that information, is how long it's going to slow down that transaction. If that's in the same data platform, it can enrich that at very low latency and not slow down the process.
Okay, great. Well, I think, Mike, that's a great way to end. So again, thanks everyone for listening in to what I like to describe as 5 non-obvious capabilities for data platforms. Mike, thanks again for taking us through this. Appreciate it.
Thank you, Matt.